Welcome to solverfy.
Problem 35.78. So we have something like a soap film, soap film. It's being held in a ring. So here's like a cross-sectional view. And so we're looking at reflected light on this soap film, or film of whatever kind of liquid. And as this evaporates over time, we see the intensity of the reflected light starts at 0, and then it goes up, and then down. And so every wavelength of light and thickness is one period of this. Because starting here, say, you go half a wavelength, you get cancellation. Another half wavelength, you go back up to constructive interference. And so what we want to know is how fast, or what is the rate at which the volume is changing of this. So its thickness is changing and its radius is remaining the same. So if we find the rate of change of the thickness and multiply it by the surface area, then we'll have the rate at which the volume is changing. So looking at this, we can see that the time from one minimum to the next is 12 seconds. And in 12 seconds, we have a change of 1/2 wavelength. So delta L is lambda over 2 N2. It's a change in 1/2 of the wavelength of the light in the film. What we need is N2 here for. Lambda represents this, its wavelength in vacuum. So our change in volume is going to be pi r squared times the change in thickness, pi r squared lambda over 2 times N2. So now dV dt, and we're told to assume it evaporates at a constant rate, which seems reasonable because the same surface area is always exposed while it's evaporating. One would expect the rate of evaporation to depend on the surface area and not the amount of liquid that's not exposed to the air. So because the rate is constant, this is going to be the change in volume divided by the time in which we're considering that change in volume. So this is pi r squared lambda times delta t, or divided by delta t times 2n2. Putting in all of our numbers, we get 1.67 times 10 to the negative 11th cubic meters per second.